Hey everyone, Zito here with the peer dependency. Today, I want to do a source code review of decron. It's a cron implementation by Matthew Dillon. If you're not familiar with Matthew Dillon, he is a Linux veteran. He's been in the community for a very long time. He currently leads the Dragonfly BSD project, and back in 1994, he developed a small program that was a Cron Daemon. And recently, as an Arch Linux user, I had the need for a cron task. I went to run the cron tab command and I realized there's no cron tab on this machine. Diving into the Arch wiki, I learned that Arch does not ship with a cron daemon by default. You need to install one. They provided a list of some implementations that are out there, among them Matthew Dillon's decron. And it was at this time that I realized I've never looked at the code for a cron daemon, and I'm really curious how one would work. So that's what we're going to do today. We'll dive into Matthew Dillon's decron source code. It's publicly available and free on GitHub. I'll share the link down below so you can look at it. I'd really like to dive into some of the aspects of process management that are really prevalent throughout this program. I think it is demonstrative of some of the best practices when it comes to multiprocessing, and specifically sort of a subsect of multiprocessing that is process daemons and background processes. I'll open Brave and pull up GitHub. We want decron. Go ahead and grab this URL. I'll cd into my temp directory. Of course, the first thing we should do when we're reviewing source code is take a look at the readme. Decron, Dillon's lightweight cron daemon. This lightweight cron daemon aims to be simple and secure, with just enough features to stay useful. It was written from scratch by Matt Dillon in 1994, and is now developed and maintained by James Pryor. In the author's opinion, having to combine a decron daemon with another daemon, like anacron, makes for too much complexity. So the goal is a simple cron daemon that can also take over the central functions of anacron. Unlike other fatter cron daemons, though, this cron doesn't even try to manage environment variables or act as a shell. All jobs are run with bin sh for conformity and portability. We don't try to use the user's preferred shell. That breaks down for special users and even makes some of us normal users unhappy. You can, of course, run shell scripts in whatever language you like by making them executable with a shebang or whatever as a first line. If you don't like the extra processes, just exec them. If you need to set special environment variables, pass them as arguments to the script. The programs were written with an eye towards security. Hopefully we haven't forgotten anything. The programs were also written with an eye towards nice, clean, algorithmically sound code. It's small, and the only fancy code is that which deals with child processes. We do not try to optimize with vfork since it causes headaches and is rather pointless considering we're execing a shell most of the time, and we pay close attention to leaving descriptors open in the crond and close attention to preventing crond from running away. Nice. That's a little synopsis of decron. Let's also jump over to the man page real quick. So here's some options for the cron daemon. We have this -s flag. This is the system cron tabs directory, and it defaults to etc cronD. These paths are the canonical cron directories in a Unix-like system. We also have the -c for the per-user cron tabs, which will go to the spool by default. The var spool directory in Linux, it's used for storing queues of data that are waiting to be processed. In a Unix-like operating system, spooling refers to temporarily holding data in a queue for later processing, such as printing or sending an email. And the var spool directory typically contains subdirectories for different services, or applications that use spooling, like var spool mail, which of course is used by the mail system to store incoming and outgoing emails that are waiting to be delivered. We also have the var spool lpd directory that is used by the line printer daemon to store print jobs waiting to be printed. And of course, and very relevant, we have the var spool cron directory, used by the cron daemon to store tasks that are waiting to be executed. And the spooling system periodically reads this data from these files and processes it. Next, we have this T flag. This is the directory of timestamps, and it defaults to the spool cron stamps directory. Cron stamps is a term that's used to refer to timestamps generated by the cron daemon in Unix-like systems. Each time the cron daemon runs a task, it will generate a timestamp that indicates when the task was executed. and the timestamp is stored in a file or log, and typically this has the naming convention that includes cron stamp. So the cron stamp's used to track the execution of the task and can be used for debugging and auditing. We might have a file like cronstamp.log that has entries of when the task executed and maybe some log output that tells us whether the task was executed successfully. So those are the basic options that we can pass to the daemon executable. Let's go ahead and hop into the main function. Here at the top, we see an interesting design pattern where Matthew Dillon aliases the extern keyword to prototype. That's all these are. These are extern variables. We see here the directories where we will be storing the user's cron tabs, the system cron tabs, and the timestamp directories, respectively. When we review source code, it's very helpful and important to know when and when not to consider something a black box. Sometimes when you're reading source code, you will come across functions or methods or classes that are complex in nature and kind of digress from the path of what you're learning about at any given time, and it can be helpful to just accept these functions do what they say they do per their name, and then just treat them as a black box. And I say that because throughout this review, there will be some functions we'll see that are self-explanatory in name, and we probably won't dive too much into those because we'll treat them as a black box. What I'd really like to focus on here is looking at how we create daemon processes. So we enter into this while loop where we use getOpt to grab these command line flags, and then we will go through each of these cases and do a little bit of configuration before we start the main loop of the program. Most of this is logging related. We won't go too much into the logging here. We might look a little bit at how file descriptors are redirected because it does have something to do with background processes. So we'll scroll down here. We see here we have these two cases, F and B. This is where Dillon sets the foreground option. So when you execute this program, you can run it in the foreground optionally. Typically, you would run it in the background because it is a daemon. So we'll go to the background case. We hop on down here, we start doing some setup. The very first thing that Dillon does is close the standard in and standard out file descriptors. The reason Dillon does this here is by closing these file descriptors, the decron program can later open them as file descriptors that point to a different file or device. As we'll see, this would be dev null. And by closing these file descriptors and redirecting them to a log file or other device, the program can run in the background without interfering with the user's terminal or other processes. This is a fairly common technique for running background daemons. Here, Dillon calls dupe2 on both of these file descriptors, redirecting them to dev null. Another use case for doing something like this is if you wanted to redirect standard error to a log file, you could call dupe2 to redirect the standard error file descriptor to the file descriptor for the log. Next, Dillon creates a temporary directory for storing the cron output. The makeDtemp function accepts a template string. We can see this here on line 203. The template string, once passed, will be mutated, and the function will compute some random string and replace the x's in the template string with that string. We also call change_mode to set permissions on this temporary directory. Here, we're making it such that the owner has read, write, and execute permissions, and everyone else has read and execute permissions. Here we check the foreground option to ensure that we are running in the background mode. And now it's time to set up the child process in which the daemon will run. The syscall fork will return less than 0 if it failed. The erroneous case here, from lines 224 to 226, we exit the program. If fork has failed, something has gone seriously awry and we need to panic. Now, if the process ID returned from fork returns greater than 0, that indicates that we are currently in the parent process. Now, hence the name fork is going to split the execution of this program into two separate processes. One will be the parent, the other will be the child. The process ID, labeled PID here, is how we determine which one we're in. If it's greater than 0, it's the parent, so we exit. And here on line 231, we see by the comment that the child continues. And next, we're going to call setSessionID to become the session leader and detach from the terminal. By making the child process the session leader, we create a new process group. And creating a new process group here allows the program to separate the child process from the terminal and from the parent process. It also makes it possible, and this is the most important part, to send signals to the entire process group rather than just the individual process. The idea here is that we want the child process to be able to have full control over all of the cron jobs that it creates in subprocesses. And by being the session leader, we can send a signal to all of them and have much cleaner job management. If you're not familiar with process group in Unix-like systems, a process group is a collection of one or more processes that have a common group ID. And when a new process group is created, the child process is assigned a new group ID that's different from the group ID of its parent. And this means the child process and all its future descendants belong to a different process group than the parent. And as a result, signals, once again, can be sent to the entire process group using the group ID rather than just individual processes. For example, a signal sent to the process group using the kill command would be delivered to all processes in the group, not just a specific process. And on line 238, where we call IO control, we're setting an option that's detaching the process from the terminal. This is similar to if you're in Bash and you execute a command with an ampersand at the end to background the process. Here on line 244, we set some logging up for backgrounded daemons, and we can see here we're calling init signals, which is going to start signal handling so we can customize how we're handling those signals, and opening the syslog. Otherwise, we open the default log file, and we also follow through with the same process of initializing signals and closing standard error and redirecting it to the log file in this case. So this is what I mentioned earlier for the dupe2 example of redirecting standard error to an actual file. On line 268, we have the alternate case where the daemon is running in the foreground. There may be cases in which the user wants to execute the daemon in the foreground, and in this case, we don't do any of that process setup that we saw before. We simply stay in the existing session, but we start a new process group by setting the process group ID. And on line 277, Dillon mentions these two different signals. The first is the hangup, and the second is the sigchild or child process terminated. And on line 282, we do some cleanup. We close all of the open file descriptors other than those standard file descriptors. So we start at 3 and we iterate until max open, which is the max open file descriptors for this program, just a configuration set in a define. And we're ready to begin the main loop. This main loop is the crux of the program. This is where we periodically check for cron updates to the cron tabs in both the system and user cron directories, and we synchronize them every second after the minute, and we have a minimum sleep of 1 second. Now in the traditional Cron Daemon, the one that's probably installed on your system if you're using, say, Ubuntu, one of the limitations is you cannot have cron tasks that run more frequently than 60 seconds. It appears this is also a constraint in decron. The very first things we do is we call these synchronized directory functions, and then we call read timestamps, and then we test the startup jobs, which only happens when cron d is started and not when the cron tab itself is loaded. So this will only ever happen once when we're executing this daemon for the first time. Let's take a quick peek at the implementation of test startup jobs to see what it's doing. In this function, we are iterating over all of the cron tabs that we have. That's represented by this concept of a cron file. It's a struct that is implemented as a linked list. Each node is a file pointing toward the next file. Second, we have cron line. This represents the actual cron tab line in each of these files. So each line would be an instruction for a job to execute with its frequency in the traditional cron tab notation. For each file, we see here on line 1148, and for each line 1152, each line in each file, we create this object called a cron waiter, and next we check if the line frequency is set to -1, where frequency is reboot, so these would be truly startup jobs. These are jobs that run on reboot. We set the job armed flag, which we will see later indicates that this job is ready. And here we employ the use of the waiter by checking if it's equal to null. The waiter in decron is essentially a way of knowing whether we're waiting on a job. One of the tricky aspects of multiprocessing, as we see here, is going to be synchronization and ensuring that we are maintaining consistency across processes, because as you know, with concurrency or parallelism, synchronization is a difficult topic, and there are some tricks that decron employs to do this, as we'll see. Really, in this function, we're not actually executing any jobs, we're just arming jobs and checking whether they are ready to run. Now we begin this main loop. I like that on line 298, Dillon has used floating braces. This is something that you can do in C. You can also do this in Go and in Rust. The basic idea here is by using floating braces, you are creating another closure inside of the function's closure, so you can declare lots of variables and do sort of setup and not have to worry about the scope of those variables leaking into the rest of the function. So it's really just an arbitrary closure that's being created here. We declare two timers. One is set to the current time, the second is a pointer that we'll set later. We also have this long, which is the diff time. The diff time is going to indicate the discrepancy between the time of the loop and the time of when jobs have been executed. This way we can catch and correct any errors, as the comment explains down below. Now we start an infinite for loop. We begin by sleeping for a certain set amount of time that is indicated by S time, defined on line 303, and we set T2 here on line 308, and then we calculate the diff time. And again, the diff time is going to be the time difference between the iteration of the loop and the time at which this block started. As this comment mentions, the cron.update file, which we'll look at momentarily, is checked to determine new cron jobs. The directory is rescanned once an hour to deal with any screw-ups. And we check for disparity using DT. Disparities over an hour either way result in resynchronization. A reverse index disparity less than an hour causes us to effectively sleep until we match the original time. A forward index disparity less than an hour causes intermediate jobs to be run, but only once in the worst case. This is our rescan counter. We use this to determine when to check and resynchronize jobs. Synchronizing in dcron is basically checking the cron updates file to see if we have any job updates. The cron updates file here stores updates and changes to the cron schedule and job configuration. Next we call check jobs. Check jobs is going to return a count of jobs. Let's take a quick look. Again, we iterate each file and each line therein. The waitPid function will wait for a child process to terminate. The waitPid function accepts the process ID of the child process to wait for, and a set of flags that determine the behavior of the wait. Typically, it blocks the calling process until the child process specified by the PID that's passed in terminates, and then it will return the child's process ID and also stores information about the child's exit status in a struct that can be passed as a pointer, here called status. The flag that we're passing in, the WNoHang flag, means return immediately if the child process has not yet terminated. So here we're really just checking if the process is still running. And down here on line 1264, we see that we are keeping account of the currently running jobs. Now we have some context for line 333. If check jobs tells us there is at least one job still running, we set the rescan flag to 1. Otherwise, since rescan is now 0, we're going to reset it to 60, and then resynchronize the user's cron directory and the system cron directory to pick up updates. After checking whether rescan is 0, we check if it's just less than 60. In the case that it is, we'll call this check updates function. Check updates is what's going to check the cron.update file in the given directory. We also pass a user override. If it's null, the files in the directory belong to the user whose name is the file. So this would be, say, if you are user Goldman, like I am, that would be Goldman's cron directory. You could also see in main we were passing the string literal root as the user override for the system directory, and that is of course because the user override for the system cron directory will be the root user. And here we actually parse the file, and we check if there are any updates. If there are, we arm the job. Finally, we check if there is a discrepancy by looking at the diff time variable and comparing it. This accords to the comment that Dillon had above about resynchronizing and fixing disparities. We see we print a log message about that. And in the other case, we actually run the jobs. In run jobs, we once again iterate over every single line in each of these files, and we call this run job function on the line or the cron job. Run job's going to perform some mail logic. If you're familiar with cron, the canonical way of using cron is that it sends mail to the administrator or whomever has been set, informing them of the job status. So here we open a file descriptor for the actual mail file, and we write the headers to the mail file, or attempt to. Even if it failed to open the file descriptor for mail, we still try to run the job if we can. And now here's the part where we actually start to execute the job. Line 58 is particularly important. We fork the new process in which we will run the job, and we call this change user function. Now, one of the critical things to understand about a cron daemon is you're not always running jobs as yourself. Sometimes you need to run jobs as a specific user in the Unix-like system in which it's running. Perhaps you need to perform some function as that specific user, and so we will specify the username in the actual cron tab, and this will end up as a member of the file struct that we'll use when we call change user. And if we can't change the user, we absolutely don't want to just assume we can run it as the current user, so we'll exit. Line 83 is interesting. We pass in the fd-clo-exec flag. This is an abbreviation for the open until exec file descriptor, and when set, this flag will cause the file descriptor that is created to be automatically closed when any of the exec family of functions are called. This is really useful in preventing file descriptors from leaking into child processes, which could cause undefined behavior or security issues. And Decron did say it's security conscious. Consider a program that opens a file and then forks a child process. If the file descriptor is not marked as open until exec, then it will be open in both the parent process and the child process after the fork, and this can result in data being written to the wrong file or the file being closed by the child process before the parent process is finished with it, so we pass this flag to prevent that. If you need a mental model to kind of imagine this, it's very similar to auto-closables in Java. And if we jump to this block starting on line 86, we go down to the else condition. This is where we complain about no mail file descriptor to log, and here we also redirect standard error to dev null. Down to line 106, we start a new process group, so the children still in the cronds process group are all mail jobs. And then line 108 is where we actually execute the job. When we read the readme, we saw that decron executes everything in a shell. And so here we're actually calling one of the exec functions to spawn a shell and execute the line cl shell member, which is the actual shell command that was in the cron tab line. And down here we do some cleanup, assuming the fork succeeded. And that's the implementation of run job. Let's summarize some of what we've learned about cron daemons. Decron works by forking a new process and then killing the parent process and then continuing to run the child as a background daemon. To do this, Decron creates a new process group and makes the child the session leader. Creating a new process group allows the program to separate the child process from the terminal and from the parent process. And this also makes it possible to send signals to the entire process group rather than just the individual process. We also learned that in Unix-like systems, a process group is a collection of one or more processes that have common group ID. When a new process group is created, the child process is assigned a new group ID that's different from the group ID of its parent. And this means the child process and all of its future descendants belong to a different group than the parent. And as a result, we can send signals to the entire process group just using the group ID, rather than having to send these signals to individual processes. And in Decron, each cron job is run in a separate process inside the process group. And this, of course, allows each job to run independently without affecting other jobs or the parent process, and also enables Decron to control the behavior of all the child processes, once again, as a group. That's Decron, guys. I hope you enjoyed the source code review of a cron daemon. I'll leave the source code link down below in the description. I'd love to hear your comments and hear what you think of Dillon's program, what you think of the cron daemon. Do you think that it could have been implemented better? Were there certain aspects of it that you found interesting or surprising? Let me know down below, and please, of course, if you enjoyed this video, like and subscribe. I have plenty more content like this coming, so if you like deep dive programming videos, source code reviews, more esoteric topics, if you will, definitely subscribe. Thanks for watching. Catch you guys next time.